I'm Brian Kim, and I'm the Director of Engineering for the Pressure Products Company. This is the first of 3 video segments about some things you need to think about before ordering or even specifying a side window. I titled these segments as Preventing Preventable Failures. The reason is that every failure that we had ever seen had been preventable. Now you might think that side windows fail because of some parameter, like process pressure exceeding the safety margins built into the unit. It turns out that those catastrophic surge events are rare enough that we had never seen them. On the contrary, every failure we've ever seen was the result of an incorrect original specification, and therefore inevitable. In other words, side windows and the processes into which they were installed were incompatible to begin with. There are 3 different types of major failure risk scenarios that you should be concerned with. In this segment, we're going to address pressure and other mechanical damage risks. The other factors that we're going to address in the following segments are actually much more significant: the chemical corrosion risk and temperature-induced failure risks. Vendors don't normally talk about these because it's difficult or impossible to make any claims of safety margins about them. But those are the risk factors that actually cause failures, and even though we are clearly a vendor ourselves, as you can tell, we are still putting together these talks to address all of those risk factors that you should consider, and not just the ones that make vendors look good.
Now, the principal risk parameter that vendors like to discuss is pressure-driven rupture. And of course, this is a significant risk parameter that we should address. This is where safety factors are applied for the most part. Over the last 10 years or so, there has been a trend towards increasing this number from a factor of 2 to something like a factor of 10. So someone thinks that enlarging this number makes things safer. Now, pressure-driven blowouts are very rare, and sometimes vendors proudly state that they never had them. We certainly haven't. But that fact in and of itself should not be taken as an indication of engineering competence. Preventing a blowout failure is just a really simple problem. Make the glass thicker. Okay? That's all there is to it. This is a textbook problem. If you open up any textbook on solid mechanics, you'll find a formula that looks like this. Here, T is the thickness, D is the unsupported diameter, and A is a constant that depends on glass properties and geometry. That's all there is to it. There are no mysterious forces that take years of experience to understand, and you can get glass vendors to make you custom thick pieces, so pressure-driven rupture is an easy parameter to address, and maybe that's why vendors like to talk about it, because you can always address this parameter. The much more difficult issue is sealing the sight glass against leaks, and that's where the biggest stresses are. In order to show you where the stresses are, I've put together a little 3D model of a side window. In this model, I have a quarter model of a simple side window made up of a soda lime glass, here, sandwiched between 2 pieces of gasket material held down by a flange. Now, for this simulation, the flange is actually immaterial. It's just here so that you can see what the whole thing would look like, but the actual loads are imposed on the gaskets themselves. The cut surfaces have been rigged with boundary conditions that create a symmetric behavior so that the whole thing would behave like a complete circle rather than a quarter slice. Boundary condition down here is a no-slip condition, and the rest of the interfaces have boundary conditions that are either sliding or no-slip. Now, these are not necessarily the most rigorous conditions you could impose, so don't write to me about it, I already know, but this is intended as a qualitative demonstration of where the stresses are rather than a quantitatively accurate simulation for a real engineering job. So the big important question is what kind of stresses we need to impose, and here we have some values. This is a brochure from a rear gasket vendor that we used, and we use these pretty often. And what you're reading here is that in order to hold 2 psi of pressure, we need to be imposing stresses of 3000 psi or so. Okay? And you can tell all of these numbers are in thousands of psi. Okay? So 2 psi process pressure, 3000 psi sealing stress. Okay? And this is the nature of sealing with gaskets. Gaskets need to undergo a plastic deformation in order to fill out the little nooks and crevices that the process fluid would otherwise escape through, and this plastic deformation requires a whole lot more stress than you need to worry about from the process itself. And this is a very, very typical picture of sealing stress versus process stress, and therefore sealing stress is really what we need to worry about. This is a simplified, not particularly rigorous simulation just to produce a picture for discussion. Now I loaded 3000 psi sealing stress on top of the gasket right here, and just for kicks I also loaded the lower surface with process pressure of 2 psi. This picture displays the von Mises stress values from the simulation. First, you can tell that the loading at the center of the glass, right here, is trivial. That's what you'd expect for a 2 psi loading. And this is where safety factor claims are made, at this relatively unloaded center. But you can also easily tell that the peak loads are not here, but below the gaskets. The place that's most likely to develop cracks is right here in the neighborhood of where this arrow is. In fact, the only fracture damage I had ever seen had been in this area. And even if you are not into stress mechanics, I'm sure that you can figure out that the gaskets are crushing the glass. Now, for those of you who are not into stress mechanics, von Mises stress is a number that can be compared to the tensile strength of a material. If the von Mises number exceeds the maximum allowable value for the material, you are going to have problems. So, how much stress can glass take? It turns out that exposure to moisture in service, even just humidity, will cause chemical degradation of the glass enough to start a so-called Griffith flow at the stress points. And since glass failure stress is related to environmental aging, glass scientists have compiled historical data over many years about how much surface stress glass can take. Normally, the recommended long-term working stress for glass is 500 psi to 1500 for annealed kind and 1500 to 4000 for the tempered kind. So this 2700 number is already above what the annealed glass can take in the long run and is on the high side for the tempered glass. There is little or no safety factors on this. And mind you, this is to hold 2 psi of process pressure. If you want to hold 150 psi, the gasket would have to be crushed harder, although not in linear proportion. But gasket sealing stress exceeding the long-term stress limits of glass is pretty common. Now, there are some important saving graces here. First, those glass stress numbers are long-term exposure values, so you might be able to exceed them for years without actually incurring visible fractures. Second, this tends to be a slowly growing crack rather than a catastrophic blowout. And third, this crack occurs outside of the process, so the crack out here won't cause any kind of a loss of containment, at least not immediately. And this is why people have been able to use this type of an arrangement for more than a century without serious problems. The rim fracture out here is usually not a life and death risk. Of course, you'll want to check that explicitly for your case. But you may have heard that you are supposed to replace sight glasses on a schedule, and you may have wondered why. If your sight window is 10 times stronger than what you need, why does it ever need to be replaced? The reason is that the safety factors are measured here, at an easy spot, and not out here, at the rear stress spot. So, inspect and replace. The final mechanical damage scenario I wanted to talk about is impact damage. As we all know, windows break, and because of this, people have been trying to come up with impact resistance glass or plastics for a long time, and these are some of the typical approaches that our industry takes towards the impact damage risk, and some of these can absorb hammer blows. Of particular mention is the fused glass, which is a metal ring that holds glass in static compression, and this can certainly absorb hammer blows. Now, impact resistance is great, but is this really a risk that you have? If you think about it, car windshields take hits from good-sized rocks at 80 miles an hour or more. So, saying that a sight window will absorb hammer blows sounds good, but in order for that level of impact resistance to translate to reduced risk, you must first have that risk. So the question you want to ask is, do you have that kind of a risk?
So, as far as mechanical damage or failure of sight windows is concerned, there are three issues that you need to think about. First is the pressure-driven blowout failure. For sight window, pressure safety margins address this failure mode. But since it's so easy to make the glass thicker, this type of failure is very rare, regardless of vendor. The second issue you should be concerned with is the gasket sealing stress. This stress is indirectly related to process pressure, since the higher process pressures require higher sealing stresses. In this failure mode, the glass is being crushed by the gaskets, and you'll see radial fractures along the rim of the glass right around here. Now, there are a couple of ways of getting around this failure mode. One is to use a fused glass, and you can see that the metal surrounds the glass, and as the gasket will be on the metal, you can apply stresses on the metal as you like. Now, this is a definite advantage of this type of a sight glass. That being said, these types of radial fractures along the glass rim are usually not life or death risk scenarios, but more of operational and maintenance issues. If this was not a major safety issue for your application, it would follow that switching to fused glass does not represent a huge safety gain, but it is usually a substantial operational convenience. The other way of getting around this is to seal on the sidewalls, right around here. A lot of our products do this, and it relieves some of the sealing stress. But both of these approaches have their pros and cons, and we certainly do not claim a one-size-fits-all magic product that's better with respect to every risk parameter than every other possible solution. Finally, impact resistance is an issue that warrants some consideration, but don't blow that out of proportion either. There are certainly special cases where impact risk is large, but before you go out of your way for something with extreme impact resistance, make sure that you are actually at the risk of being hit by a penetrating projectile, like something that would crack your car's windshield. There are other risk factors that you have to address that we're going to talk about in the future segments, and your safest choice might wind up accepting a lower margin on these mechanical parameters in order to secure a greater margin on other parameters. Now, if you call us about our side windows, our applications engineers are supposed to bring up all of these risk factors together, and we certainly want our customers to make holistic risk minimizing decisions. But whomever your side window vendor is, make sure that you explicitly address all of the risk factors, not just the ones on the sales brochures. That's it for now. I'm Brian Kim for the Pressure Products Company. Thank you for watching.